Hello, everyone, and welcome to my final project presentation. My name is Sean Oliquer, and today I will be presenting my project on real-time object detection in video. So to start us off, the problem statement that I'm looking to solve here is how can I leverage computer vision techniques, specifically object detection, to detect common signage that can be present in our factories, which will lead to improved safety of our automated systems, right? And in this case, as you can see in the picture here, something akin to an AMR or an autonomous mobile robot. And the background for this is really that I work in the aerospace and defense industry. And in a nutshell, right, A&D is essentially a manufacturing company, right? So we are putting together, planes and helicopters for the U.S. government. That's kind of, in a nutshell, what my company does. But producing those, those safety critical parts, right? We're trying to do those in a more efficient and fast way, but to do that, we have to keep, safety in the forefront of our mind. So how can we have these robots moving within our facilities in a safe manner for, our employees, but also for, the robots themselves, for our products, right? So there's quite a few avenues of safety that we're kind of looking here. So the proposed solution that, I'm throwing out by utilizing the object detection model YOLO V5, right? Kind of, state-of-the-art object detection, we can detect and identify road signs from a custom online data set. And I'm using road signs because the data would be my data within my factory would be, either proprietary through my company or potentially classified. So I'm kind of using this driving data set, detecting road signs to be an analog for a robot looking for signs throughout our factory. So a high-level overview of the process that I put together, and we'll get to that kind of at the end of this PowerPoint presentation as we jump into the code a little bit, is really to download the pre-labeled data set, right? And that's going to be of those road signs, of those videos and those images, along with their attached coordinates and height and width measurements for the bounding boxes. We're going to load those into our YOLO V5S model. That's a small model that we'll be using. We're going to train that model, and then once it's trained, inspect the validation data. Is our mean average precision score good, or do we need to kind of modify any hyperparameters, anything like that? Once we're satisfied with that, we're going to go to the testing data set, compare those map scores to the training and validation sets. Let's visualize some results. And then lastly, let's fine tune our model. Can we get, are we missing any signs, and can we get higher object detection scores, right? Do we need more data? What tweaking or optimization might need to take place? So before we get too far into this, I just want to do a very quick introduction to the tasks that exist in computer vision. And if we start on the left up here, kind of in this cat and dog diagram, classification is kind of what you think of when you first get into computer vision, right? You work on a CNN and you're trying to detect if this is a cat or is it a dog, right? It's one single class or class of thing within the image itself. If this is a cat, this is a dog, this is a plane, this is a horse, or whatever it might be. That's kind of the, the starting point. There are a few others, but I'm going to touch on object detection because that's, essentially what my project is about. So within this, right, there are, two dogs and a cat. So we need to look at this image and detect, of all of the potential images in this, what are they? So that is significantly harder than this, because this looks at, gives this entire image as a single input and says, hey, this is a cat. Where in this case, if you gave this whole image that, there could be a tree, a chair, two dogs and a cat, we need to look at this image, find out where objects are, and then once we know where they are, detect what they actually are, right? And there are a few others, but I'm not necessarily going to go into them. You can kind of infer what those might be based on the pictures here, but essentially just trying to highlight that the object detection is, a significantly harder challenge and kind of an advanced form of this classification, right? We want to do multiple classifications in one image. And some common examples, you've probably seen things like this, this one especially, from self-driving cars, right? It needs to detect other cars, bicyclists, so we don't hit them, hit the cars, the person on the bike, right? We need to detect the traffic light. Is it a green light? Is it a red light? Am I stopping or starting? Another image of dogs and cats, this person on a horse, a dog, and kind of a truck in the background, right? So in a nutshell, that's what we're trying to do. So object detection originally kind of started with what are called region proposal networks, or in simpler terms, double shot detectors. So they look over the entire image, and it's going to say, hey, of this image, what is background? Essentially, there's no image there. This is the grass in the background. This is the house in the background. Whatever is not important. And then it's going to look at everything else. So kind of this middle region here and whatever this thing on the left is. And those are going to be proposed region networks. And then within each of those networks, it's going to conduct object detection. So it's called a double shot detector, because it's actually scanning the image once to find where those regions are. So this middle region, this left region, et cetera. And then it's going to do object detection on each one of those to find out what the objects are, right? So it's very good at object detection because those region proposal networks, or those region proposal boundary boxes, can be very small, right? So if there's another horse in the far background, it could just have a really small region network around that, and then it would detect that it's a horse in there. So it's really good at small objects within the image. The downside of double shot detectors is that they're slower than single shot networks for obvious reasons, right? We have to scan the image, and then for each of those networks, we then need to conduct object detection. So if we're looking to do this on video, right, which is kind of the theme of my project, we actually want speed to kind of be on the forefront of our capabilities. So that actually brings us to single shot detectors. And this is what our YOLO model are. There are a few others like MobileNet that we're not necessarily going to jump in this lecture, but there are quite a few, right? So in a nutshell, very high level, right? We're going to break our image into n by n grids. So in this case, we have an 8 by 8 grid, and then within each one of those grids, we're just going to say, is there an object in here? Object, 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 object. It's going to just do classification within each one of those grids, right? And in this case, we kind of see this blue grid here detected this cat on the floor. And then the single shot detector kind of, not necessarily a fault, but a unique aspect of them, right, is that this box here probably detected a dog, and this box detected a dog, right? So we could have multiple bounding boxes around this dog. So then what it's going to do, it's going to say which one of these boxes is really capturing the most dog information, right? And it's going to kind of compare that to, the labeled bounding box information that we have available while we're training. So yeah, there could be, we have other images kind of later that will show this dog could probably have like 50 boxes around it, right? But the great thing is that we're doing this all in one pass. We're going to detect all of these. We're going to find all of the bounding boxes, and then of those bounding boxes, which are the most relevant to capture the most information for that object, right? So again, kind of coming back to the biggest incentive for using single shot detectors is speed. So like I said earlier, the technology that I'm using specifically is YOLO object detection. So YOLO is you only look once, right? So again, looking back, single shot detectors only look at this image once, find the bounding boxes and show them, right? So essentially, it is a convolutional neural network, right? And it's made up of a head, a neck, and a backbone. So the backbone here is, in essence, it's a CNN akin to the encoder of an autoencoder. So a good method for optimizing your YOLO algorithm or your YOLO model itself is actually to train an autoencoder on a very large data set, right? Something like ImageNet or COCO. And then just kind of remove the encoder, and that's your backbone for this model. And then you fine tune the neck, and then, what is the actual predictive head of this, right? So the neck is actually using the dense connections between your quote encoder backbone here. It's going to predict probabilities and the bounding box coordinates for your image, right? And then your head is actually just a final output layer for prediction. So something akin to like a softmax predictor here to say, hey, here are my probability lists of this is a cat, this is a dog, this is a train, and this is a horse, right? Something like that. So specifically, if we kind of get more specific on each one of these, I'm using the YOLO V5 model. There's not a ton of great information about all of the, the version models. The YOLO versions 1 through 3 was kind of all by the original author. And then 4 was, kind of a spin-off, but it still had, a paper aligned with it. And then version V5 actually is same as V4. There's no, new functionality. It was actually just created by a company called Ultralytics, and it is really just a PyTorch implementation of YOLO V4. So the great thing about that is that Ultralytics just made it incredibly easy to use. Sorry about that. It's all in PyTorch, right? You just kind of pull from their GitLab or their GitHub repository, and then within a few lines of code, you're up and training a model, which is incredibly convenient, right? With the V4 model, which is the one I originally used, it's in TensorFlow, but the actual backend is in a C++ darknet. That was, getting myself way too into the weeds to actually produce results or actually get a model training properly. So YOLO V5 works in PyTorch, incredibly easy to just download the CUDA version that you need to train on your home GPU, which is nice. So the dataset description, I kind of touched on this a little bit earlier, right? The backbone of your model can be trained on something really big, right? So, Coco has, 2.5 million, labeled objects within 320,000 images, right? So this is, something big data in terms of actual object detection in a data set. So the pre-trained, if you wanted to use the pre-trained model of YOLO or YOLO V5, it is actually pre-trained on the Coco data set, which is great. The specifics of my data set that I used, right? Because I want my project to be an analogy of something that I can directly take from this project and port over to my work, right? Just kind of swap out the data set with my proprietary data set on site, is actually from a European road sign data set, right? So I'm trying to mimic what my robot would be driving through the halls of my factory or through my factory floor. I need to detect safety signs, or I need to detect go, no-go signs, stuff like that, right? So that one's actually located here, and something we'll get further into as we actually check out the code itself. If you would like to, right, I'm not going to spend a ton of time here, but if you would like to, there's actually a lot of tools for annotating and bounding boxing your own data sets, right? And I think label image is probably the easiest one to get up and running. You just, download this GitHub link and, run the executable, and you're basically good to go. Super easy. And the great thing is that the output can be a few different outputs, but you can actually output within YOLO format itself. So you come in here, train a few thousand images, right, in an hour or two, kind of just quickly go through this, bounding box what they are, and then you have your training set up and running. So this is what I plan on using on my actual work data set in the future. So before we actually get into the model itself, how do we know that we've scored a good object, right? And the essence is really a score called the intersection over union. And that's, we have our ground truth box here, right? That's the red box. And then we predicted this yellow box. So the intersection over the union would be this small box percentage, whatever that area adds up to, over the union, kind of the entirety of all of the boxes, right? And that score is how good we're doing. So if we detect that an object is this, right, this score is 83% IOU, right? Within our backend, we actually, one of our hyperparameters to determine if we're detecting good images or not is actually an IOU threshold, right? So if I detect something that is an IOU of 0.08%, right, that's pretty bad. So we're going to actually get to ignore that because it was a misclassification, or it's only capturing this cat's ear, right? So we're actually looking for something that's capturing the most of the ground truth image itself. So the results on the training data set, right? And I only used about 1,000 to 2,000 of the actual images for training and testing. So we're not getting great map scores here. A state of the art is around 58 to 60% on the Coco data set, which, with us only using a very, very small set of data to get around 40 to 41 or 2%, right? That's not actually that bad. But ideally, we would like to capture more data, right? And just feed our data set with more road signs, just to, more data, the better generally. And if we look at this, this one on the right, the bottom line was actually estimated to be the background, right? So we're actually confusing a lot of our signs with the background, which in this case is not very good, right? So in my use case, that would be my robot potentially running into a wall or going into a safety marked zone that the robot should not be going into, right? So increasing our data set, generalizing our data set, maybe additional augmentations, so it learns other visibility factors of our signs, of our road signs, could probably alleviate a lot of this, right? And the great thing, YOLO V5 actually, once you're done training and testing, actually outputs a lot of these visualizations. And these two are here, are a kind of a smaller subset of like 15 to 20 various images and metrics that just kind of come free as like a bag of freebies. So looking at the test predicted objects, right? So we can actually see quite a few of the signs and the traffic lights, and we can see in our testing, right, on this right side, we missed one here, right? That's a do not enter sign. We captured one of the traffic lights in this bottom left, but we missed another traffic light, right? So that's where we can kind of see the effect of stuff like this, right? We might just be missing it as it's detecting it as, quote, not an object or background, but we're actually like if that were a red light and we just did not detect it, that could be, a very serious issue. So let's see if I can play this video here. So this is the real-time detection. This would be, kind of from the robot's eyes. So this could be like a safety marker. We want to go on the right side of that safety marker to not go in where someone is working, stuff like that, right? So we can kind of take this driving scenario as an analogy for a robot in a factory. So the pros and cons to kind of close out the presentation here, right? The pros of YOLO, very quick. In some cases, you can get up to like 140 frames per second. And that's just for the small model. We are using the YOLO V5S, which is the smallest model, or maybe the second smallest. I think they have a Nano as well. And the network is very generalizable, right? So you can find a lot of different pictures with various juxtapositions. So a small horse in the background of a field, or a person sitting on a horse right in the foreground, it's going to detect a lot of those, right? And it can change to your needs. It's really adaptable and extensible, and it's really easy to get up and running, which I found just very, very critical, especially in my job. Getting a kind of a minimum viable product up and running, and then iterating over that is very crucial to having successful products. The cons, right? So sometimes, right, and not quite as good as the double shot detectors, is that sometimes it can overlook very small objects, right? And that may be the case of what it was doing with the traffic lights that we saw earlier. Maybe they were just a little too small in its pass. And yeah, that kind of goes to the comparatively worse localization error compared to double shot detectors, because we're only making that one pass and we're taking the best of those bounding boxes. We're not necessarily honing in on that object first and then detecting it. The actual comparison there of the map scores is slightly worse than double shot detectors. But again, we're kind of trading a little bit of that for speed. All right, next steps in future iterations, right? I want to try the new version of YOLO, right? They have some kind of better optimizations. They're up to, version 7 again. It seems like a lot of people are just, releasing object detection and calling it YOLO. So really making sure you're capturing or downloading the correct GitHub version with a paper assigned to it, preferably, so you can validate their results is kind of crucial. Next, I would like to actually have a bigger data set. So my homegrown data set at work is actually going to be capturing, live, live data feed off of the robot itself, right? Having someone kind of drive the robot through the factory floor, and then going back through and capturing, 5,000 to 10,000 images for the custom object detection model. Automated hyperparameter tuning would be nice to kind of run this initial through something like Determined AI, right? So we can get, are we using enough epochs, too many epochs? Do we need to change the number of bounding boxes, right? So in the example we looked at earlier, it was kind of an 8x8, but maybe making that smaller on our training data set might help capture some of those smaller objects. So thank you. I appreciate your time here. I am going to go through the my code really quick, just to demonstrate how easy it is to get PyTorch up and running with YOLO v5. So we're looking at just kind of the PDF output of my code demonstration here. So we can see just a little better view than just kind of running through my Jupyter Notebook or my VS Code. So yeah, we're going to import Torch and utils, download the YOLO v5 repo directly from GitHub, right? And that kind of comes with all of the code, the pre-trained models on the back end, and some command line, some CLI commands that allow you to train and infer or detect kind of right out of the box, which is really nice. So one thing we want to do, and I highly recommend getting a GPU, or GPU access, right? Whether that's through Google Colab or a local machine. I'm lucky enough that I have a GTX 1070 on my desktop. So having quite a bit of RAM and a GPU kind of makes short work of this, which is really nice. You can, if you want to, if you're following through this, you can actually run this code here to download the entire Cocoa backend data set. It would be a good exercise to actually run through all of that, start with a fresh YOLO model, kind of set it running for 1,000 epochs or so on the Cocoa data set, and just take off that backbone of that model and then bring that into your custom data set. I did not. I used the pre-trained model, but this would be a really good exercise for learning how they did that. Go to this website right here and download the European road sign data set. That's kind of loaded under the back end into my images data set folder. And it looks something like this. We saw some of those previously in the presentation. Here would be the sign that we need to detect. And just a note, right, those actually bounding boxes are not on the image themselves, right? That would be almost too easy to kind of to work with, I suppose, or not necessarily beneficial. So they're actually stored in a text file that says, this bounding box is at 350 and its height is 80 by 80, right? And then, yeah, like I said, right, the YOLO v5 repo, because it's through the Ultralytics, right, they made it extremely easy to get up and running. So you just, kind of run a magic Python command, train.py, and then you give it some parameters, right? We want to use this YAML file that actually defines our data set. That's going to say, hey, these are all the classes. This is what they are. Here are the parameters of the YOLO v5 model. Batch size of 8. I'm going to call it this model here. And then, in this case, I'm only going to run it for 2 epochs. But, in my training and testing that I showed earlier, that was trained on 300 epochs. But I just wanted to show a demonstration of what your output could be. So it's going to be here, right? I'm using, 2 gigs of my GPU memory for, these 2 epochs. And we can see our map score, kind of slowly increasing just over these first 2. Right, this first one is kind of expected to be pretty trash, but we slowly, actually pretty quickly, by an order of magnitude, 2 orders of magnitude, increase in the map score in just 1 epoch. So that's pretty great. And then, kind of similarly, if we want to just detect or run inference, it's just detect.py. And then you just say, what is the source of your, your testing image or your video or your folder of video or a folder of images, right? So in this case, right, this is just, I want to detect on 1 image, but in the PowerPoint video, I just gave it the entire video of that. So that would just be akin to running a video on my robot of it going around. And I want to test on that whole video, and it's going to spit out the results folder of all of those images of that video with their corresponding bounding boxes attached, which is really cool. So we would see something like this, right? But it would be kind of one contiguous video set of my robot kind of going throughout the factory floor with caution signs and go, no-go signs kind of highlighted and detected in the image. So yeah, like I said earlier, something like this is what YOLO is going to give you. So we get quite a few results, right? We see possibly some validation overfitting, possibly, but the training is actually looking to continue. The training loss is actually continuing to decrease and decrease and decrease, but our validation loss, maybe around 200, 250, is looking to flatten out quite a bit. And our object loss, or how good we are at actually detecting our objects, is actually starting to increase at 1 150, 200. So we might just be overfitting. Again, I'm only using about 2,000 images, so that's well within the realm of possibility here. We can see our map scores as well. So, on our 2,000 images, in this case here, we have two different map scores. This one here is a little more indicative because it's kind of in the bounds of, 0.5 to 0.95 bounding box score, right, of our IOU score. So it actually drops significantly if we're taking out all the ones that are, kind of like ace in the hole, super easy scores. So this one is a little more indicative of what, our testing data looks like, right? So that's really all I have. I appreciate your time and thank you for watching my presentation. Thank you.